All right, folks, let's get started. So I just have a little bit of information to say, and then I will let you guys have the majority of time today to work on your in-class exercise. So last time we talked about... Turn the lights off. Maybe by the end of the semester I'll figure out what the light switches do. So last time we talked about, we introduced spline interpolation, and we said the purpose of spline interpolation was to allow us to do what? Why do we do spline interpolation? Not just because Dr. Kinney told you to, but what's the purpose of spline interpolation? Say that again? It's helpful. For what reason, though? Yes, sir.
To determine a value like between given values you have.
Right. So to determine to make some predictions or to determine things that we don't know already. So if we're talking about the example that is related to your in-class exercise, we measured a bunch of temperature, or we took a bunch of temperature readings, we measured density, and then we measured kinematic viscosity, and we were fitting some spline curves to the temperature and the density data. And then we said, what is the air density at 350 and 450 degrees Celsius? So once we're done creating our spline curves, we're going to get three curves, right? We're going to get, we were to draw a picture of our data. We have what data on our x-axis of this plot? Is it the temperature data or the density data? Louder. Temperature. So we have temperature on our x-axis, and then we've got our density on our y-axis. And then I just gave you the kinematic viscosity data for, bonus extra information. So we have these four data points. We have temperature at 200, 300, 400, and 500, something along these lines. We've got the four data points, and we've got our density values. Oops, I put that backwards there, going down instead of up. Something like this. And how many splines can we fit to the four data points that we have? 3. So we have one here, we have one here, and we have one here. And those are the things we're trying to solve for, right, with our linear system equations. We wrote out all those lots and lots of equations so that we can solve and figure out the coefficients for each one of these curves that we have, right? So at the end of the day, we're going to get three curves, and they're going to all be in the same form because we said we were going to fit what type of spline to these curves? What type of polynomial are we fitting to this data? Cubic. So cubic polynomials have the highest exponent of 3, so they all kind of have this general form like this. And since we have 3 of them, we're going to have 3 curves. One with subscripts, coefficients A1 through D1, A2 through D2, and then we have a third one, A3 through D3.
The y, is it like y0?
This is just our generic polynomial equation. So it could be any x and any y that we plug into this equation. So this is polynomial 1, this is polynomial 2, and this is 3, which on our graph corresponds to 1, 2, 3. So if after I've solved for my spline curves, I've solved for those 3 curves, I have values for A1 all the way through D3. And I now want to predict. I now want to get the Celsius. What do I do? Yes, sir.
Could you use for loop to get the exact one we need because we have like 400 degrees, 400.
What would we do with our for loop though?
Like the interpolation between the two values.
Well, didn't we just do that? We got the interpolation between the values, right? So where would 350 degrees Celsius be on this plot? Would it be between which 2 points? Which two? The x0, x1, x2, x3. Where does it fall between? X1 and x2, because we said 300 and 400 are x1 and x2. So this one is my 300. This is my temperature of 400. So my 350 would fall in between there. So if I know that I have a temperature of 350, what could I use to predict the density that corresponds to a temperature of 350?
What, 350 and formula 2 and solve for y?
Right, so basically on my graph, I just want to draw a line up here and figure out what that point is on that line. And so just like John was saying, all I have to do is I take my 350 and I plug it into equation number 2. For the x value, I get back a y value, and that's my air density. Make sense? What about 450? Which Spline equation would I plug 450 into to get the air density? 1, 2, or 3? 3, because it's between our 400 and 500 values. What if I wanted to predict a value, the air density at a temperature of, I don't know, 600 degrees? Somewhere way out here on my temperature scale. Do you think that's a good idea or a bad idea? John's shaking his head now. I would concur that that's a bad idea. When we do spline interpolation, we really only know about the information we have between the data points we were given. It's not good to kind of what's called extrapolate or move beyond that range of data, because we can get completely wacky predictions beyond that range of data that we have. So it's not a good idea to do extrapolation, but you can use this to interpolate or predict values within your range that you have. So that's how we do that. So that's kind of all I have to say today. On your in-class exercise, what I want you guys to focus on is solving for your 12 unknowns. So writing your linear system equations in matrix form to solve for those 12 unknowns. If you have time to do the prediction at the 350 and 450, then that would be awesome too. That will be helpful for your homework because you're going to likely have to do that in your homework. So I will let you guys have the rest of class to do that. If you get done with your in-class exercise and you don't want to get started on your homework, then you are welcome to have an early Friday. Other than that, I will be here until, whatever, 3:20, whatever class is ever.
I'll let you off,